Productive, intelligent and perfectly adapted to its environment, nature is both efficient in its use of resources and fascinating in its variety of motion forms. Natural phenomena are also at the heart of Festo's Bionic learning network. With 100 product innovations per year and 2,800 patents, Festo sets the pace for its 300,000 customers around the world in the field of factory and process automation in their quest for maximum productivity. Festo employees are currently researching how automated motion sequences can be made more efficient and energy conserving in future. For example, with the aid of Bionics. Engineers and designers work hand in hand. They make use of what nature has optimized in millions of years of evolution and transfer these principles from nature to the technical products of the near and distant future. The Bionic Learning Network is also part of Festo's commitment to technical education and training. In cooperation with universities and research companies, Festo promotes ideas and initiatives which go beyond the company's core business of automation, and which may open up new and interesting application fields for the future. The prototypes utilize cutting-edge technology from Festo. Bird flight was the inspiration for the development of the AirRae, and yet its form resembles that of a manta ray, a form which has been continually streamlined over thousands of years. Filled with helium, the extremely lightweight ballonette behaves as if it were swimming in water. The remote-controlled hybrid construction uses the so-called fin ray effect, similar to the flapping wings of the manta ray. The fin ray effect is a construction derived from the anatomy of the fish fin. It enables the AirRae to make flying maneuvers similar to those of birds. The fin ray effect has also found initial practical applications in the field of automation. With the aid of Festo's Bionic material Gait, 7 parts can be carefully sorted in a single step. A completely different drive concept has been realized with the Bionic Airfish. This project combines bionic refinement with an unusual drive form originally conceived for space travel. The flow-optimized structure is based on the shape of a penguin. The innovative bionic plasma undulating drive in the stubby wings simulates the mechanical wing motion of birds, but without moving parts. Flow phenomena also play a major role in valve technology. The Bionic Airfish serves as a prototype to examine the reduction of flow resistance with ion beams. In the case of the humanoid, the task was to transfer the biomechanics of the human musculoskeletal system to a technical construction. The key element for the realization of this aim is Festo's fluidic muscle. Already a permanent feature in production systems, the fluidic muscle is proving to be a universal tool in a surprising number of new applications. It's simply a completely new type of pneumatic drive. Its properties are similar to those of a real muscle, but it's operated with air. When the fluidic muscle is filled with air, its diameter increases and the length contracts. This enables flowing and elastic motions. The initial force of this artificial muscle is extremely high, and its dynamics resemble those of the human muscle. The humanoid can either follow pre-programmed motions or be controlled in real time via a data suit and data gloves. This means it can be used in places which are either inaccessible or too dangerous for humans. Eric's arm also utilizes the fluidic muscle. It attempts to simulate as closely as possible its human role model. With the aid of Eric's arm, even more complex movements will be made possible. 30 artificial muscles move the bone structure and joints, a construction not encountered in this form in the world of technology. In combination with Festo's latest piezo-proportional valves, this technology enables precise control of the construction's forces. Coordination of the muscles and valves is made possible by cutting-edge mechatronic systems and software. Eric's arm is also of great interest to the future of robotics, as it can interact almost naturally with humans. It glides almost silently through the water, the Kuda. The AirRae Kuda is a remote-controlled, pneumatically driven fish. Its head houses the electronics and pneumatics, which control the S-shaped motion of its tail fin via two fluidic muscles. Two further muscles control the steering movement. Once again, the fin ray effect provides the necessary propulsion. A bottle housed inside the fish supplies compressed air to the artificial muscles and the air bubble. Sensors measure the depth and control the valves. The air bubble is flooded with water to make the fish dive, or with air to make it rise. Even more agile is the Aqua Ray, a remote-controlled fish with a water hydraulic drive unit whose form is modelled on the manta ray. The ray is regarded as a highly skilled underwater acrobat. Its wave-like motion provides maximum thrust with a minimum of effort. By using new types of elastic materials and a deformable skin, it's possible to accurately emulate the swimming kinematics of the natural model. Uses in marine research applications are therefore feasible, as the Aqua Ray can glide through the water without disturbing the natural environment. Whether on Earth or in space, in the depths of the ocean or high in the sky, the new drives of Festo's Bionic learning network are all inspired by nature. In this way, we can develop new approaches for energy-efficient products of the future. But the researchers of the Bionic Learning Network also have another aim. They want their projects to make technology exciting for young people. For only enthusiastic young technicians and engineers can one day turn these visions into reality.